Okay, we're live streaming now, just waiting to click a button. Got the button clicked. All right, so we're on page 91. Let's start with the screen share. We're talking about systems. Okay, so there we go. So one of the things, okay, we've got to get past the quiz. We'll worry about the quiz some other time. Now, I'm looking at this stuff right here on the top of page 91. All right, so many problems we're going to see you have two blocks, or in this case, two blocks next to each other. It turns out there's a cool shortcut we can use that applies to a subset of all physics problems. It does not apply to all physics problems. And before I waste any time explaining the shortcut, I want to emphasize it is crucial. We need to be able to treat the two objects as a single system if they have the same acceleration. So if we have two objects that do not have the same acceleration, we should not be treating them as a single system. So in this case, if you take two blocks and you push on them, they're probably going to move with the same acceleration, right? Unless one of the boxes is being crushed as it smashes into the other one. But in general, or like in this case, you could say, well, if I view this direction here that I'm drawing with this giant arrow as the rotation direction, basically they're both moving clockwise in some sense, then you could view these things as a system. All right, so let's get that going there. And so let's scroll down here and let's maybe take a look at let's look at 5.27. This is a good problem to start with. So what we're going to do is, and if you have trouble with this after the fact, you could do questions 5.25 and 5.26, and you can kind of get a feeling for these. And I wrote up detailed solutions. So that said, we're going to start with 5.27 here. So I'm going to take a second, draw it on my board. You could do the same. All right. Just going to get my head wrapped around this problem. 5.27. Okay. Force with magnitude F is applied to the front block. Okay, got it. And let's take a second and let you try and draw your FBDs without looking at the solutions. I know you could look at the solutions. Give it a shot, give it a try, and then find out if you could do it. Try to draw the FBDs. And I'm going to draw 4M on the left side. And you don't have to try and draw the arrows to scale because that's going to be pretty tricky here. So to give you an idea of what I'm thinking about, I started right here like this. Okay. And so in this case, I'll get this thing out of the way. There we go. Again, it's going to be very difficult to draw these to scale because there's so many different vectors. So I drew this force F. I drew a normal force upwards from the ground on block 3. Notice I wrote, this is supposed to say 3 mg. That was a little sloppy. Okay, so the idea here is there's going to be different normal forces involved. It would be a bad idea to call this N or even F subscript N. Here, it makes sense to have a subscript that identifies which normal force it represents. Because this block had a 3 in it, I'm using normal force 3. All right. Let's keep going here. Maybe let's do 4M next. Somebody, let's see, what's one force on 4M?
The 4mg.
4mg, I love it. And rather than try and draw it to scale, I'm just going to get it done. What else?
You got T.
T, which way?
To the right.
To the right. So think about it. T is the tension in this green cable right here. There's tension pulling backwards on 3 and forwards on 4M. All right. All right, good. Another force on 4.
Normal force between 4M and M.
That's right. There's a normal force this way. Now, this is tricky. Remember, 4M pushes to the right on M. M pushes back to the left on 4M. So I'm going to call this normal force 1,4. Now, this is the convention I use in my solutions. Is this the only way? No. Are there many other correct ways? Sure. But I think you will find this useful. This N subscript 1,4 corresponds to the normal force between blocks 1 and 4. Okay, so this relates to both 1 and 4. That's why it's got subscripts 1 and 4. Here, this is only on block 3, so I don't need to worry about it. I just write an N subscript 3. And that is the standard that I use in the solutions. You could totally call this N subscript A, N subscript B, N subscript, but I think these subscripts have more meaning, and therefore it's easier to kind of remember what they mean at the end of the problem. Okay, so there's got to be something holding this up. It's not falling through the ground. So what's a good name for that normal force based off what I've been telling you?
N4.
N4. And so if we do this trick where we always use both subscripts when it's between two blocks and then only one subscript when it's from the floor on the blocks, this will work out and we can keep everything organized and we never have two things with the same subscripts. All right, let's go over here to the middle block. Oh, wait, is there anything else on this? Let me think. There's a tension. There's this one. There's that. There's this. Okay, I think that's it. There's no friction in this problem. We're in chapter 5. Okay, on the middle one, what are the forces on the middle one?
N14 to the right.
Oh, good. I guess I kind of did it all. This is the tricky one right here. N14. Now remember, you might be saying, wait a minute, shouldn't it be N41? I push on you the same amount you push on me, right? I push on the whiteboard pushes back on me the same amount. So here, these normal forces have the same magnitude because they're an action-reaction pair. So if I could even make that pop out a little and make it purple, although I don't know how much the purple is going to show up. So the idea here is 1 pushes on 4 to the left using a normal force. By Newton's third law, 4 pushes to the right on 1 with a normal force of equal magnitude. This is not the normal force. This is the magnitude. That's the direction. Being even more clear, N14 equals N41, but N14 does not equal N41. See the difference? If you think about the vectors, you can't change the subscripts. If you think about the magnitudes, you can. Okay.
So is it okay to label it either way?
Yes, you could have called it N41, N14, but the idea is use the same label here because the magnitudes are the same. So to be clear, Dom's asking, can I just say this? Could I just have used N41? Absolutely. So basically choose one of those two options there. And I think I'm going to go back to 1.4 just because that's what we started with. Not because it's the right way, it's just a way. Good. Other questions? All right. Now check this out. We could also label this with an acceleration, and maybe they're all accelerating to the right. How do I know that? How do I know they're accelerating to the right? Could the acceleration be 0?
It says it's initially at rest.
Mm-hmm.
So therefore it has to be accelerating if it's moving.
Okay. How else could you know that? If you pull on this, we expect it's going to go that way, but how do we know that acceleration, how do we know it won't be at constant speed?
Is it because the Fbd for math 1, like you can see the vector going to the right, but there's nothing balancing it out?
Absolutely. You could see that right here, right? There's a force to the right on this one, but nothing to the left. What is a common force that could oppose this motion that we ignored?
Friction.
Friction. If friction was present, which it is in the real world, then it's possible you could pull this and it moves with constant speed. That is the next chapter. But if there's no friction, just like Dom said, we see clearly there's no possible way you could oppose this force, right? Without friction to slow things down and oppose this and then, okay, great. So that's the idea. If it's a frictionless scenario and you apply a net force in one direction, it's going to go that way. Now, here's where we could see this even easier. Let us draw the system Fbd. So imagine everything is in one blob here. So we kind of put it all together as one blob. If we do that, for the entire system, what is one force that acts on all of those blocks? And I should be careful.
F.
Oh, yeah, F. F acts on them, right? It is an external force. It is outside of this purple blob I'm going to draw here. I'm drawing like a fuzzy boundary. So I'm curious about any forces that are exerted by objects outside of that fuzzy purple boundary that I just drew, outside of this circle. So F is one of them. What's another one?
N total.
N total. So there's some kind of normal force upwards from the ground. Now this one, we've already used N1, N3, and N4. What we haven't used is an N with no subscripts. So I'm going to use that for the system Fbd. So the total normal force from the ground. And then one other force, somebody else.
Gravity, mg.
Not mg, but
that'd be m total g.
yeah, which in this case is how much m?
Oh, 8.
Yeah. So that is where students make a mistake on a quiz day as well. They're like, oh, I know it's just mg, but then they forget that some blocks have 4m, some blocks have 3m. So watch out for that trick. You can see Dom just made that mistake right now, but he probably would have written it down correctly on his paper. But yeah, You get the idea. Watch out for these numbers in here. These are the things that students forget when they see these blocks. And these are the things I do basically on test day, just so not everybody's doing the same problems, right? What if I made this a 2M? And then on another test, what if I made this 2M and that M, and, you know, et cetera. So it makes it pretty easy to rearrange the problem so they give distinct algebraic problems. But yeah, okay, so just be aware of that. Now we're done. And here, the System Fbd helps us understand this acceleration issue. There's a force to the right that is unbalanced. There's a net force in the I-hat. We can tell immediately the system must accelerate to the right. So this is called a System Fbd. It is very useful if you can use it. And we see that the key thing that you can get out of this is notice immediately, if I write the force equations in the x direction for the system, F equals, well, that's the only force. What should I write here? The force is in the x direction. This comes from the arrows. Got it. What goes on the other side in a force equation?
It's 8ma.
8m, because that's the mass of the system times the acceleration. Right? And so we see this is the trick in this problem. It's very easy to get the acceleration from a System Fbd, which you could then use that known value of the acceleration in these other Fbds to find a normal force or the tension. All right. Now, in this problem, these forces are called external, right? They came from outside the fuzzy blue blob. Everything inside of here is internal. Now, I should be careful here. These three upwards normal forces are also external on each block, and they actually relate to this total normal force. Obviously, you could add up these three to get that one. So, but for example, these green arrows, the tension, that is inside the purple blob. It's pulling backwards on one part of the system, forwards on another part of the system, and they balance out. That obviously matters because, you know, if we didn't have that rope there, we couldn't treat it as a system, and this would be a very different problem. So, but yeah, how about this purple normal force right here? Normal force between 1 and 4. That one is included inside the system boundary. As a result, we could ignore these internal forces. Notice these two cancel out, and these two cancel out in the System Fbd. These three add up to that one, and these three add up to that one. All right. So, all right, I'm going to pause for a second and see if there's questions about this trick of doing the System Fbd. Let's see. All right. Doing good. Let me see what I want to do next. Let's do a pulley problem. Okay, so let's look at 5.31 on page 92. Actually, let me see if I got another one here. Let's look at 5.40. 5.40 on page 95. 5.40. It's a similar problem. Where are we here? All right. So we're going to look at this problem right here. Okay. So it says M1 is at rest on a frictionless incline, and now we have two masses. This is a different version where one of them is M subscript 1 and then the other is M subscript 2. So we're going to try and figure out this stuff right here. Now, when you see this problem, we should do a free body diagram for each mass. All right. And since I'm just going to get this picture drawn up and I'm going to walk you through it myself. All right. So you can start kind of thinking what you would do. You could even try it. but I'm going to catch up in a minute. So we got, this is 5.40. And we've got this here. Okay. So here comes kind of a, this is getting a little bit more advanced because we've got multiple blocks. We've got an angle. Also, we're not told which way this thing accelerates. And so we want to kind of make some assumptions here. And that's the part I wanted to show on screen, right? So when we first see this, it says, come up with this answer. Now, let me look at that answer really quick. It's saying, it does tell us. It says, assume up the plane is positive. All right, well, that makes things a lot easier. So if we know that, I'm telling you this is the positive direction. All right, and so now you may not be used to this, but I want you to learn how to do something the way I recommend, and I'm going to show you right here. Imagine my hand is this coordinate system. I got to scoot it back so I have some room here. Imagine my hand is this coordinate system, right? Right there. I'm lining up my thumb with the string in the direction the way this block is going to accelerate. Watch what happens as my thumb follows the string around the pulley. When I do that, that's the same thing as saying the coordinate system rotates with the string, and this becomes the new x-axis, and this becomes the new y-axis. At first, you probably think this is a really dumb idea. I could tell you what, I wouldn't be telling you if I thought it was a dumb idea, all right? Here's the advantage. If you do this correctly, your algebra gets simpler later, and this prepares you for dealing with circular motion, which is, that's a sloppy looking A. There. So the idea is, it's very cool to do this trick because now, if we assume this is true, everything is accelerating in the same direction, the x direction, okay? And so when I write my force equations, I know that acceleration in the y direction is 0 for both blocks. That's one less thing to screw up. Also, my accelerations are both pointing in the positive direction on each block. This is very cool, right? That means I don't have to worry about minus signs on the right side of my force equations. So if I do this, right, let's try and draw the FBDs using these two coordinate systems, all right? These two coordinate systems. So FBD1, I know gravity is going to pull straight down. But I don't want to write mg. What do I want to write?
M1G.
M1G, because there's two different masses. So you've got to get used to doing subscripts. Okay, somebody other than Esteban, what direction does the normal force point on one? Straight up, straight down, to the right, to the left? Just kind of describe it in words.
Perpendicular to the slope.
Yeah. So like this?
Going up.
Yeah, good. All right, just messing with you. Good job. Now, in this problem, how many normal forces are we going to have?
2.
2. Where's the other one?
Oh, never mind.
Yep, it's only 1. So that means I don't need to worry about subscripts on this one. But if you wanted to, we could call this n subscript 1. Okay. So you could either use no subscript or n subscript 1. All right. Anything else acting on block 1? Is there friction? I think there was no friction, right? It's chapter 5. So,
Professor.
yeah, go ahead.
Why aren't you drawing the FBD like the according to the axis? Like
These are the
friction.
forces. The forces, you just draw how they appear.
Oh, okay.
The coordinate system will tell us which of those forces needs to be split up.
All right.
So, right, the normal force is going this way. mg is straight down. We can't force it to line up on the coordinates if they don't line up. Good question. Good
Okay.
question. What's the other force on this?
Tension.
Tension, right? There's a string. So we said in the past, we're going to use tension for that force. All right. Now, what Dom was saying is, how come these aren't on the coordinate system? Well, remember, our coordinate system, we said, is this way. So which force needs to be split up?
M1G.
M1G. And to make it fit better, I'll label the this side. So does that look right? For splitting it up?
No.
No. The hypotenuse is no longer the vector. We need the vector to be the hypotenuse. So you got to go this way. Remind me, what's this angle up in here? Is it theta or is it 90 minus theta?
Theta.
This is theta. If you don't remember, this is where that trick comes in handy. If you draw a skinny triangle, it's pretty obvious this is an angle less than 45. So was the original theta. This is the 90 minus. If you have trouble seeing that, you go back to the original picture, you draw it, and you say, well, if this is that, this is 90 minus, and that makes this theta. Again, we have a right triangle here, so this one is 90 minus, and this one is theta. So that's how I got this angle down here is theta. Okay. All right. So I'm going to do the next FBD. You could try and race me to it. FBD 2. All right. The upwards force on that one is from the string, so that's tension. Downwards force here is M2G. All right. Now, you might be wondering why it's okay to say this tension equals that tension, or why it's okay to say this acceleration equals that one. I'll go into that in a minute, but for now, just trust me that it seems to be true for this type of problem. All right. So now I'm going to write down the force equation for block 2. Well, shouldn't these balance? Shouldn't I just get T equals M2G?
No.
No. This block is accelerating. This is only true if it's not accelerating. So I was trying to trick you. So what we should get is T minus M2G equals M2 times A, right?
Yeah.
No.
That's negative t.
Look at this. We said we would use this coordinate system, right?
Okay, yeah, that makes sense.
So I was trying to sneak one past you again. These are the two most common mistakes that students make, the two that I just did. What happens here is you get so used to writing these and then you get busy. We didn't draw the coordinate system right next to it here. If I did that, I think you'll see right away the mistake, and you probably already did. Remember, we said it's accelerating downwards with magnitude A. So what you could have done is, there are two correct ways to do this, right? But here's the thing. The coordinate systems, who cares really? But this should be clear to you. The force that points the same way as A should have the same sign as A. I'm going to say that again. The force that points the same way as A should have the same sign as A. And if you get used to checking that after you write your equation, you're going to make fewer mistakes. Or if you make them, you'll catch them. I'm going to say it a third time. The force that points the same way as A has the same sign as A. Don't screw it up. All right. So when we do that, now we get some different equations, and I'm actually going to go this way. So now we see that in this case, I'll just label this as the direction it's accelerating here. So write the force equations for each of these really quick. See if you get it before I do. That's what I got. Sorry, it's a little sloppy. That's supposed to be a letter M. It's a little better. Gosh, it's still sloppy. There we go. That looks a little better. All right. So, are there other correct ways to do this? Sure. But I'm doing this for a reason that will become hopefully cool in a second. Now, if you're not sure where the sine and cosine came from, remember, I could see that most easily right here. This side right here is adjacent to theta. So that's going to be M1G cosine. This side is opposite, so it's M1G sine. Notice this arrowhead right here shows it's against the positive direction. Or if you look at this, T should have the same sign as A. And in this case, M1G sine should be opposite the sign of A. Whoops. These two should have opposite signs. Minus sign right there. Let me scoot this over so it looks prettier. There. Looks a little better. All right. Questions about that? check this out. So now what I could do is I could put this under here and stack the equations. Give me a second to do that. So I'm going to take this x equation and stack it under the other x equation. These are both from the x-axis. Remember, we called this x and this x. So when I do that, I get t, whoa, what? T minus m1g. Oh my gosh, this is hard to write from this angle. I'm having trouble. Sorry. All right, let me bring this back up. Okay, so what I did is I just wrote this equation again over here. Now, I'm just going to add these two equations. I'm going to add the right sides and the left sides together. So in this case, when I add these, what force drops out?
T.
T. All right, so I'm left with I'm going to write it this way. I get M2G, the T's drop out, minus M1G equals M total A. Now, M total here is M1 plus M2, right? The total mass. Essentially, what we have done is we have got a system FBD force equation without having to understand the system FBD. This procedure works all the time. The system FBD works some of the time. So it's really useful to know when to apply the system FBD. However, we could see that you can get a system FBD result without too much effort if you follow this strategy over and over and over again. This strategy relies on a couple of things. One, let's go back and look what we did here. And let me get the whole picture. I know it's going to get a little small here. The idea was this. First thing, use the rotated coordinate system that follows the string, okay? If we do that and we line up the x direction with the positive acceleration, so if we do that, we end up with down here what we found was this system equation with the internal forces dropping out. If it helps see this a little bit better, remember, the tension is actually internal because it's going this way on this way. Whoops, this way on that one. Let me make it about the same size. The idea is the tension is pulling 1 in the forward X, 2 in the backward X. It totally seems plausible why it drops out. All right. So, and now, all right. So I'm going to pause for a second and see if there's any questions about that. That is one of the reasons why we want to do this. The other is it gets you used to circular motion. Let's go look at the question and see what we were supposed to figure out. A common strategy in all these types of problems is to first draw the FBDs and then work it out. Okay, I don't know if you could tell, but we were one line away from getting that equation. If I divide both sides by M total, I get the right answer and I factor out a G. How would you get this answer? How could we figure out the tension? Let's say we wanted to get the tension. What should we do?
You use your solution for acceleration and plug it into one of the ones that have tension in it.
Exactly. So we found the acceleration in terms of the masses and the G's and the all that stuff. So then what you do is you could get this A, solve for it, plug it in up here, and you solve for tension and do a bunch of algebra. All right. Nice job. Okay. So now I promised I would mention something about what conditions have to apply for us to use the same tension and all that. So let me show you where that is in the workbook in case you want to see this stuff. Trying to do things in a little bit different order just to keep you guys awake. Oh man, yeah, we'll come back to that one. Right up here, this problem, notice there's parts A through L. I did this. This is the problem you can do if you're new to this stuff and you haven't done this in a while. This is where I explain all the assumptions. So what assumption makes this valid? What assumption makes that valid, etc. So you could obviously look these up, and but this is probably what you might have thought to do very early on, with the possible exception of rotating these coordinates. Oops. That shows you why I chose to make this the X direction here. Oh, looks like I need to flip that, don't I? Oh, wait, did I? Yeah, I need to flip this one right here. But the point is the Y direction here and the Y direction there are the same direction. This problem, I never notice that because it's always in the Y direction. So yeah, the X doesn't matter that it flipped. Apologies for that. All right, but here's the idea. If you want these two strings to have the same acceleration magnitude, obviously they have different accelerations. One is up and one is down. But if we want the same acceleration magnitudes, right, that is the string is inextensible, right? If the string moves 1 inch on one side, it will move 1 inch on the other side. So the motion is exactly the same. All right. It says acceleration is constant. That is this part where it's massless. Okay. If the string, if you use a chain, a heavy chain, you're going to be transferring mass from this side to that side. And then the accelerations, basically, you would have variable masses, M1 and M2. The mass of those would be changing because the string is moving from one side to the other. If the masses are changing, we know the acceleration would change. Just look at the result of the last problem. We saw the acceleration depended on the masses on each side. All right. And so finally, what's the last one? T1 equals T2 is just some tension. So that one, actually, let's use a different color for that. Let's do it this way. And so here, what is the assumption that makes these two tensions the same? That's this, the Pulley information. So if we assume we have ideal pulleys and an ideal string, you might see that in some books. An ideal pulley would be one that has negligible axial friction and negligible mass. Sometimes you'll say it that way. And then you could have an ideal string. Whoops, where'd it go? Oh my gosh, zoom. There we go. So those are the key. So any questions about that while I'm writing this up here? There's an ideal pulley and an ideal string. That's what allows us to say they have the same acceleration magnitudes and the same tensions.
The coordinate system is actually correct.
Oh, is it?
Yeah.
Oh, did I draw my... Oh,
I had to do the hand too, just to make sure.
Whoops. All right, that's good. I must have drawn my first one on the page incorrectly. Sorry about that. Yeah, so there, okay, so the X is pointing this way, and that's why it's, yes, you're right, it is correct. And I'm sorry, I drew something incorrectly. I was in a hurry to get to something else. Good job. All right, other questions about that? This is a pretty good problem to go through as you're learning, okay? I want to point out something that is done right here. And we're going to go back and look at our previous results, okay? Do your expressions for A and T make sense? Okay, and so in this case, let's go back to the one we were just working on. I think it's one more page, right? Here's the results. Let's think about this. does this result right here for acceleration make sense if M2 is much bigger than M1? If M2 is much bigger than M1, what happens to this? We get G times M2 minus something small all over M2 plus something small. Well, these small parts don't really matter, right? This part we can ignore, and this part we could ignore. It's small. These cancel out. Does that answer seem reasonable if M2 is large compared to M1? What do you think?
Yes.
Let's think about it. If you tied this on to a feather, that's supposed to be a feather. 2 should drop like a rock. This is the acceleration magnitude when you drop like a rock. And remember, we said this thing was accelerating down that direction with magnitude G. So all of these things make sense. Cool. You could do the same logic if M2 is really small, right? What if M2 is really small? This is going to drop out. This will cancel, and we get negative G sine theta. Does that sound vaguely familiar? If not, it turns out that is the result that we discussed earlier when we talked about blocks being on a ramp. Remember when we were doing chapter 2 problems and I said the acceleration was G sine theta? Whoops, negative G sine theta, right? So it's negative G sine theta up the plane. That makes sense. That's equivalent to positive G sine theta down the plane. Again, we were told the plane is positive. That's why I drew my arrow up the plane, but we get a negative value. All right. And here is one more kind of advanced trick. Give me a second. Think I could just get it. All right. So let's do. There we go. So you could just barely see both of these problems. Again, this is page 95. The upper problem and the lower problem are pretty similar. This thing is called an Atwood's machine, a pulley with 2 blocks on it. It's a classic physics problem because it forces you to understand a lot of things: tension, acceleration, coordinate systems. Okay, it's a very good introduction. But look at this problem down here. It looks very, very similar for what value of theta? What number could I plug in for theta to get problem 539?
90 degrees.
Think about it. Is 90 degrees right? That would be like this, right? That is the same problem. So this is the advanced trick. We've done a general case. If we plug in 90 degrees, we should get these cases, right? Take a second to look at it. Plug in 90 degrees. Do you get the correct answers for problem 539? Sine of 90 is 1. We get the same answers. Now, at first glance, you may say, who cares, dude? I'm just going to do one problem and be happy. You're right. And that's a good way to do it. If you could solve the first problem, that's great. But your ability to check your work adds up over time. When you become a junior or a senior level student, you are going to want these extra ways to check your work, right? If this problem was really nasty, it really is nice to be able to say, okay, well, let's do a simplified case. What if you are a computer science major, right? This gives you 2 test cases to code. So you could check and make sure 2 different codes match up. You could make this code run and make sure it works because it's easy. Then you add in the angle and verify you could make that code work. It's called doing baby steps. If you try to do the hardest, most general problem first, you often fail and get frustrated. So as we get higher and higher in the class, we want to get ways to check our work, and checking one problem against another problem is the strongest possible check you have. It's much stronger than checking the units. I guess we should check the units here. When we check the units on this one, let's get back up to right there. Let's get down here. If I want to check the units on this one, it looks pretty ugly. Let's check the units of A, the upper one. Well, notice what I've done here. If you plug in kilograms for all the stuff with the red dot, you'd have kilograms in every term and they would drop out. Aha, we could use kilograms, we could use grams, we could use pounds, we could use whatever we want. Pounds is kind of a bad thing because pounds corresponds to a weight. But even if you did that, you'd still be fine. That'd be like multiplying by an extra G in each term. So that's cool. And sine theta has no units. This whole thing in the circle I'm about to draw has no units. The term out front has the same units. We see this is a classic way to write a physics problem. Something with the correct units times something with a yawn. I mean, no units. Okay, let's check the other one. When we check the units on the other one, look at this. I'm going to pull out an mg. It's m1g. Going to get rid of that. Notice this, I know, is a unit of Newton because I've seen it so many times. That means the rest of it, give me a second. The rest of it in that circle there should have no units. Well, on the bottom, kilograms plus kilograms equals kilograms. I have kilograms in the top. This stuff has no units. We are good to go. I see the units check. I see that 5.40 reduces to the result of 5.39. I feel very confident in my work. I check what should happen if M2 is large compared to M1. What if M1 is large compared to there? You could plug in all these different cases and check. Again, going back a few pages, if you go to page 92 and look through this one, that's what this stuff is talking about. So if you want more practice at home on all this stuff, 5.28 is a good one to kind of walk you through and make sure you have this on lock. Okay. Now, what are we seeing here? Physicists are annoying to talk to because they're always checking their work. And so when the problems get really complicated, that's really useful. So this is why it's very difficult to deal with physicists all the time. Well, that and I don't know. Yeah, we could go on and on about that all day. The fact remains is this is a good strategy for you to succeed in a physics class. You want to check your work in as many ways as you can before you show it to your boss and look stupid, right? So imagine you're working somewhere on the job. You could make a plot. You could check the units. You could check this scenario versus a simplified case with a simpler angle. You check every possible case you can before you show it to somebody else. That way, if you did make a mistake, it's something small, not something big. And everybody's going to make small mistakes here and there, right? So yeah, all right. Enough said on that. All right, questions on that? All right. Let's look at one more problem, and then maybe we'll take a short break. I like this problem right here, 5.32. This is on page 93. Okay. Get that all on there. All right, page 93. The idea here is this problem looks really nasty. However, if you set up the problem correctly in the method that I just described, this problem is not that bad. Now, I'm going to go to the solutions for 532 just to show you, to kind of think what you would do for this problem. I'll give you a second just to kind of wrap your brain around it, all right? Tell you what, I need some more water. I'm going to get some water. You think about this problem. You could even sketch it out if you want, okay? All right. Hopefully you've had a second to look at that. Let's go look at the solution 532. So here is kind of what I was thinking on this. And notice I use this rotated acceleration. I'm going to go back to the original problem and just talk about the acceleration really quick. Remember, if you want to focus on the answers, you could do that. You've got the solutions, but let me just show you that coordinate system trick. Whoops. Right, in this case, I'm going to assume if you're pulling this one, it's going to accelerate to the right. And so then you follow the string around. That makes this one go this way, right? And we'd expect if the front one, if number 4 accelerates to the right, this one will accelerate down the plane. Notice I use a rotated coordinate system. This one would be this way. This one would accelerate to the right, and then kind of wrapping around here. Whoops. This one should accelerate up. So that is kind of the trick here to make all these equations look the same. We rotate the coordinate system, that thumb lines up on the string, and it works out. Okay, let's go back and look at the solution again. So that takes care of why I chose this, 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 and that. Are other choices valid? Absolutely. However, you will probably see why this is really useful. Now, notice I drew all the forces. Now, here, this tension was the same, but there's no reason to think the tension, a different string has the same tension. So there was different strings in the problem. So if I could go back and show you that, why did I label these T1s and T2s? Let's go back and talk about that. Oops. Right? So what I'm saying here is there's a red string, What did I use for the middle one? Blue, I think. Blue string. And then there was a green string. So there's 3 different strings here. There's no reason to assume the strings have the same tension. We know that the tension is the same in a single string if the pulleys are ideal, which we are assuming, and the string is massless and inextensible. That's what makes us assume that these have all the same acceleration and it's constant. So those are all factors at play here. We're assuming an ideal string and an ideal pulley, which allows us to do this trick. This is all of everything in that string is T2. Everything over here is T1. And everything over here is T3. All right. Let's clear that out and go back to the solution, see if there's anything else. Oops, this one. So that's where I got those. And then there's some components. Notice you got to be careful. Here's a theta. There's a phi. Be clear. And so when you write all this stuff, we get an X equation. And if you stack them and add them, look how sweet this is. Let me just do this just a little bit. There. If we stack them and add them, that's where this is, right? That's where those equations came from. Look at all the internal forces, the tensions dropping out. And so in this case, I don't need to use the System Fbd, and I get a result for the acceleration almost instantly. As the problems get more complicated, and notice there's another check on my work. I get mass total times acceleration on the right side. So this is a sign this is working right. It's a check on your work. The more checks on your work you have, the less times you take this class. That's the bottom line. All right. And so from there, all right. Whew. Oh my goodness. Any questions so far? All right. And then we're actually getting pretty close to the end here. Let's see. What do we have? 20, 35 minutes. Let's take a 5-minute break and then we'll come back and do 30 minutes. All right. So space out for 5 minutes and then we'll come back and we'll finish up. All right. So a couple of fun little topics to finish up, and then we're done with this chapter. So I'm going to start with a quick screen share. So in this case, this is problem 5.35 on the top of page 94. Now, I'm mentioning this one. I think you might like this problem now. I think we're finally at a point where you can tie the graphs of position and velocity versus time to force problems. So in particular in here, what kinds of information can you get out of a VT plot?
Can you get acceleration and position?
Exactly. We could get, well, you should get acceleration and displacement,
Yeah.
right? Yeah, which relates to position. But so you could get the acceleration at each point here, right? So at this point, you could say, like, for example, here, acceleration is less than 0, negative slope. Here it's less than 0, negative slope. And here it is a greater than 0, positive slope. So, all right, so great. We've got all this stuff, and you could use that to answer these first questions, right? Velocity, positive, negative. But now you could also take a number for that acceleration, and we know, for example, in this case, tension minus mg, and then you could say in this case equals ma, and then you could let a be a positive or negative number. So if a is a positive number, right, it's accelerating upwards, you'd expect the tension should be bigger than mg when it's accelerating upwards, and vice versa. If the acceleration is downwards, you'd expect a negative number, and mg would be bigger than tension. The fact is, we see that you could use a video and the tracker program, and you could analyze the motion. From that motion, you could get a VT plot. From the VT plot, you could figure out an acceleration and get a force. This is really cool. And some of you are hopefully going to do that in your talks when we do this in lab tomorrow. You could do your preparations. Maybe this makes a little bit of sense. So I thought I'd mention that. All right. Let me check another problem. This is one you probably haven't seen before. Constrained motion with pulleys. So I want to talk about this briefly because some of you are mechanical engineers, and this is kind of your bread and butter. So and everyone can gain from this a little bit. So it turns out you could make this system here. Here's what it looks like. You take a brick. Okay, let me you take a brick, you get a cart with some wheels, you get a little pulley, they look just like that, you get another little pulley, and you hang a mass here. And so when you do that, a simplified model of this system is this up here, right? We're going to ignore friction. How do we ignore friction? We're actually going to use a cart with little wheels on the bottom. So it rolls, but the wheels have negligible mass, blah, 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 blah. Okay. So in this case, let's try doing parts A and B, right? So take a second to think about that. Take 30 seconds. That one moves distance h, right? That means this string goes distance h. So what's going to happen to M1? Do you think it will move distance h or something other than h?
I don't think this is correct, but my intuition's kind of telling me it's going to move 2h.
Okay, so let's see. If this pulley moves this far, so let's say we put the pulley right here. Now I probably should have used a smaller value, right? That means I need to use more. Whoops. Okay, let me clear this. Let me use an eraser here. Actually, let me use a smaller distance so it's easier to label. I think you're right. It's a little bit tricky, but let's say this one moves distance h. That means the pulley moves that far. And so I need to take up that much string on the top and the bottom, right? So what happens is if I pull 1 inch of string here, that's equivalent to pulling 2 inches of string for the lower block. Now, obviously, this string here, this upper string doesn't move at all, but I need to take 1 string here and, I need 1 inch here and 1 inch here, and that adds up to this block having to move 2 inches. So that is correct. Nice job. Well, now let's propagate this downwards. If it moves twice as far, what do you think is true about the 2 acceleration values?
M1 is going to accelerate twice as fast.
So A1 is twice as big. So now everything else is the same. You could do a problem where you call this acceleration A and this acceleration 2A. So instead of having the masses be m and 2m, you could have the accelerations be a and 2a. And that's totally fine. And that is the trick here for these types of problems. It's not that bad. Now, another thing that's kind of interesting here, you could do an FBD for the left pulley. So for this pulley right here, we could actually do an FBD on that pulley. So, well, I know there's a string pulling this way, and there's a string pulling this way. Here's the pulley, right? Now, obviously, it's the same string, but it's pulling on it twice, right? So that's, maybe I should do this in color, right? That is from this lower half of the string, right? If the string pulls M1 to the right, M1's pulling to the left on the string. And likewise, if the pulley's pulling to the right on the string pulls to the left on the pulley, right? And so this, I'm going to call tension 1. And we see that that tension appears twice. The other string, I'll call that T2, is pulling on this. Now remember, T2 is actually attached to the axle of the pulley, but essentially the pulley and its axle. So maybe this would be better if you could see that there's like an axle here that it's pulling on, okay? And I'll show you, if you want, you could look down at the picture down below, and that shows you what it might actually look like with physical objects. But so when we do this one, right, in this case, now there's some mass of the pulley. You might be saying, well, shouldn't there also be an mg of the pulley? You're right. We are going to assume, however, that this term is negligible. And I do that by using really big M1 and really big M2. If M1 and M2 are really big compared to the mass of the pulley, this actually works out. And so with about 2,000 grams for mass 1, or 2 kilograms for M1 and 0.25 kilograms for M2, the pulley's mass is totally negligible. So this is a feasible problem. I normally do this in lab, in lecture all the time. Okay, so in this case, notice what we see about this, right? Which way is this pulley accelerating? Which way is that pulley accelerating?
To the right.
With what magnitude? Is it A1
A2?
or A2? Yeah, it's A2 because it's attached to string A2. So you could write the force equations for this, and we would get negative 2T1 plus T2 equals mass of the pulley times A2. But what did we just say about the mass of the pulley compared to these other things? What do you think will be true about this term right there?
So A2 is approximately,
Not A2, this entire term. The mass of the pulley is so small, no matter what acceleration you have, this is going to be approximately 0. A2 is definitely not 0. This thing is going to move. But the idea is the mass of the pulley is small. When you do M2G, it was small. Well, now I'm doing M2A. A is often smaller than G. It's going to still be smaller than those tensions. Again, I'm saying, look, up here, I said M2 or mass of the pulley times G was negligible compared to these tensions. Well, if this acceleration, even if it's on the order of free fall, which it's not, it's going to be less than that. This is still small compared to those tensions. As a result, we see that the orange tension is twice as big as the pink tension, or T2 ends up being twice as much as T1 if you solve that equation. So this, okay, so I kind of went through all the hard stuff there on this one. This one's pretty confusing, but it's very interesting. Essentially, it's like using leverage, right? Mechanical advantage. There are times when you want to make systems like this where one string connects to another pulley and you get double the force or half the force or things like that. You can get double the acceleration, etc. Interesting, right? All right. I'm going to pause. Questions on that? It's pretty cool, right? So again, this is what it looks like in the real world. I'll try and make a video of that when I get the chance. It's on my list. I just haven't had time. So let's be realistic here. I generally don't stick this type of question on an exam, but I think you should still go through it and learn something from it, especially because you can learn some interesting stuff going through these cases here. So it gives you a chance to practice. Yeah, and I've done this in class many times. If you look at the reaction time and all these things, you can get this right to within 10% time in and time out. So it really works as long as mass 1 and mass 2 are significantly bigger than these pulleys, which are like 10, 30 grams, somewhere in there. So that usually works. All right. If you're curious and you like this one, right, maybe you're a mechanical engineer and you want to see this, you should try this one, right? It's similar. Or maybe you've heard of a bosun's chair or a block and tackle. So this might be what that looks like. And here's another one. This is kind of a fun one for me. I've always wanted to make one of these. I just haven't had the time. So I want to make one of these so kids can pull themselves up. And you can literally lift yourself. So you can see Chewy and Zool down here. Right. But the idea is if you use enough pulleys up here, a kid can lift themselves. The problem is making sure they don't kill themselves by pulling themselves really high and then letting go and falling to the ground and killing themselves. So that's why I haven't gotten around to making that for the science show yet, but it's on my list and we've got some pulleys. So who knows, maybe in the fall, that'll be something we get to, but all right. And I like these names, Chewy and Zool. I don't know why I found two names with a UE in it. So, all right. So far, so good. If you're a mechanical engineer or physicist, you probably would like those problems. Everybody else, if you have to choose something to skip and you want to skip those, I understand. All right. Just get good at one block and two blocks without all these weird extra constrained motion. All right. We've got just enough time to introduce friction today. So let me go to a problem here. 15 more minutes. Let's just keep cruising along. If you haven't already done so, better get workbook volume 2. Okay. All right. So page 99 has got all the information you need and the equations that we need. Friction is tricky. This is now chapter 6. Okay. We're into chapter 6. Let's start simple. If you have two surfaces that are moving relative to each other, there's this equation you can use. That's when you can use this equation. If you have two surfaces not in relative motion, but something in the problem indicates they're on the verge of slipping, you could use this equation. The K here means kinetic. So this is mu subscript K, or kinetic coefficient of friction. That's what mu K means. Okay. Mu subscript S means static coefficient of friction. Now, on some problems, there's no indication it's on the verge of slipping. In those cases, you have to resist this temptation. All right. Now, I'm going to go into some problems and I'll clear this up more, but I just want to say there are a few things worth emphasizing. In general, normal force is not always mg, and it's not always mg cosine theta. This is the most common mistakes I see on test day is students like, I don't know what the normal force is. I'll just plug in mg cosine theta. The way you get a normal force in every problem is do an FBD, write a force equation, and figure it out. Okay. Friction usually depends on the normal force, but not always. Remember, sometimes we can't use this equation. Most times, either this or that applies, and we see friction depends on the normal force. That's not always true. Now, typically, the coefficient of friction mu static, the static coefficient of friction is usually larger than mu kinetic. In many problems, physicists get lazy and just say, let's just call them all mu. Okay. Pet peeve of mine, friction and mu are not the same thing. F is frictional force. Mu is frictional coefficient. So if you've got your book handy, maybe underline this line right here, bold this. Okay. Next, which way should friction point? Shouldn't this be obvious? Evidently not. Many times I've asked students which way friction points with a multiple choice question, and they screw it up. So do not underestimate frictional forces in FBDs or in force problems, okay? Let's consider this example right here, all right? A block is pushed along a table and it accelerates to the right. We're going to assume block 1 remains on top and it doesn't slide relative to block 2. Check out this chain of reasoning. Look, block 1 must accelerate to the right. Why? 1 is not moving relative to 2. Hopefully that makes sense. 2, there's only one force acting horizontally on block 1. That's got to be friction from 2 on 1. Therefore, that friction points to the right. Otherwise, block 1 won't accelerate to the right. So let me pause. Any questions about these first 3 bullets here? Does that make sense? All right, I'm going for it. Interrupt me at any time. Okay, just unmute and say, dude, I don't, okay. Next, nothing in this problem indicated it's on the verge of slipping. It is inappropriate to use this weird equation. Okay, fine. Now, from Newton's third law, friction from 1 on 2 points opposite friction from 2 on 1. So, like we said before, there's a frictional force going this way. I'll call that F(1). Why? Because we're told these blocks accelerate together, and that's the only force that could cause it to accelerate that way. By Newton's third law, there's a friction going this way. Friction 2, 1. Again, the subscripts 2 and 1 mean between blocks 2 and 1. We know, to be clear, F2 on 1 vector is equal and opposite friction 1-on-2 vector. But friction 2-1 magnitude should equal friction 1-2 magnitude. So again, you could use the subscripts 1-2, 2-1 interchangeably. Okay. Okay, finally, there's another frictional force. Block 2 is sliding to the right relative to the floor. That means there's friction from the floor. There's this way. So there's another frictional force here. And we see that in these problems, there's multiple different frictional forces pointing multiple different ways. And it's very easy to get in a hurry and just flip one of the arrows and screw up the whole problem. Okay. I'm going to pause while this is all there. Any questions about that picture? So cool. Here's a final thing. Consider relative motion or the tendency to move between two objects. So friction always occurs between two objects. Think about which way the objects would move relative to each other and let that be the guide to which direction friction points. Okay. Now, if you are worried about this and you think you're a little bad at it, let me show you something here. This page 101, literally, you're not supposed to do FBDs and force equations for this. It's literally thinking about friction. So this entire page, page 101, is to practice and make sure you could read a problem statement and identify which direction friction should point and which coefficients. Some of these I deliberately left vague, so I don't want you to waste a lot of time on these. I want you to read, take your guess, check the answer. Read, take your guess, check the answer. Don't write anything down, just read it and check. And when you do that, these represent a large number of the types of problems we're going to see in this class. Okay, so all right. So that's good. That said, let's take on a nasty problem. Let's try 6.3.5. Okay, so let's try and write these down, and I'm going to draw this on the board with you. Okay, so 6.3.5. This is on page 100, the bottom of page 100. I'll just get this fired up. And remember, if you don't have the fractional problems in your workbook because you have an old edition, you can find all the fractional problems on the solutions webpage in the rightmost column. So you go to the solutions, look in the right column. The problem statement for 6.3.5 is in there somewhere. Okay. So if you don't have those, go look for those if you have an old version. All right. I'm going to pull here with some angle. We're not told the acceleration. Oh. Min M2 to cause slipping. All right. We got 6 minutes. We can get the FBD done, right? That's what matters. Okay. So here's the guts of the problem. We're pulling this way, and then we're asked this. Determine the minimum M2 to cause slipping. Now, when you read that, let's try and figure out which way things move. If we don't know which way they're moving, we'll never get the directions of friction right. So based off this, which way do you think these blocks are going to move? I want the minimum M2 to cause slipping. Let's go back and look at the problem one more time. See if there's anything else in there. What does that make you think? Which way is it going to slip?
Should it slip to the left?
So when I read this, think about this. If you put in, we need a minimum amount to make it slip. So that means we're gradually increasing 2. Agreed?
Okay,
If
it's
we
just the other way.
gradually increase 2, at some point it's going to get so big it overpowers this zombie and pulls the zombie to his death. Oh, wait, it's already dead. So, yeah, so that's what I read when I see that. So I'm going to assume it's going to slip this way. Now, maybe that's, yeah, we could discuss whether that's appropriate, but let's just go with it for now. Yeah. So we're going to expect this one to move this way. Now it says minimum to cause slipping. When I see those words, what I think is it's just about to slip. So this is equivalent to on the verge of slipping. So when I see this problem, I think, okay, this must be on the verge of slipping. That tells me something. What does this tell me? If it's on the verge of slipping, maybe I'll put this in here now.
Then friction equals mu static times normal force.
Yes. Friction for block 1 equals mu static for block 1 times the normal force on block 1. Now, in this case, there's only one normal force. There's only one block, so we could erase these subscripts 1s. Right? Block 2 is hanging here. It's in free space. It's not having any friction. Obviously, there's air resistance. We're going to ignore that. So this case, sweet, we're good to go. This tells me something else. If it's on the verge of slipping, how quickly is it slipping? If it's on the verge of slipping.
Not at all.
Not at all. What's the acceleration?
0.
So the idea here is this. When you see the wording in a problem, you have to make several key assumptions. And this is what kills students in these problems. In a problem where it's minimum to cause slipping, you're supposed to know that implies it's on the verge of slipping. And that tells you, well, if it's on the verge of slipping, set acceleration to 0 and set friction to mu static times the normal force, do an FBD, draw the force arrows, write the force equations, do everything the same as chapter 5. This is a key first step. All right. That is the difference there. Let's read another problem. So again, you could draw FBDs now. Well, which direction is the frictional forces? Let's at least get that. So we expect it's going to move this way. So what direction is the frictional force on 1? Somebody other than Esteban. We're told we're using the minimum mass 2 to cause slipping. We expect it to slip this way. Which way is friction on 1? Go ahead. Take a shot at it.
It's to the left.
Yeah. And so notice, now we could see, whoops, that's supposed to be a letter F. I want you to be careful in these problems. There's lowercase f, which we're going to devote strictly for friction. Capital F's are going to be forces applied by strings, zombies, whatever. Okay, so now that doesn't mean it's the right way to do it. It's just the way I've chosen to do it so that I'm always doing every problem the same. That's it. All right, so far so good. Hey, it's time to go. Let's stop the live stream. But yeah, chapter 6 is going to get very hard very quickly because friction, it gets hard very quickly. And then the second half of chapter 6, by the last half of Monday's lecture, we're going to be doing circular motion finally. All right, so we're starting to get into it. So If you have not caught up, make sure you get caught up on your workbook problems. You should be done with chapter 5 by the end of this weekend, or maybe by Monday night. Okay, maybe Tuesday or whatever. But yeah, ideally you would be done with workbooks chapters 1, 2, 3, 4, and 5 within the next few days, within the next, say,